interference patterns, and now we're taking this gas cloud and this other gas cloud, we're overlapping them, and we're taking a photo of that, and what you see what comes out is this beautiful interference pattern. And now what I want to make you aware, this is scale now, this thing is 1 millimeter. Okay? This is not anymore the microscopic realm of atomic physics. This is really something you can almost measure with your ruler at home. Okay? And it's like, I always say, this is such a fantastic experiment. I think it's like, turning your water faucet on at home, adding water from the side to it, and suddenly you see that water vanishes in some spaces and other places get amplified. I mean, you would be shocked to see that. And this is like as shocking when you see that the first time. Okay, this is how the labs look. Okay, this is the reality. What I'm hiding from you, what we have to do to make it all work out. And when we have the school children come to visit us, they always think this is the storage room for our optics, but it's not the storage room. This is the actual experiment, arguably one of our more complex ones. So you have this array of mirrors, of fibers guiding the light from this table to the actual experimental table. That's not even the experiment you're seeing. That's just the table where we generate all the laser light we need. We guide it over to the experimental table. Yeah. And so it's complex, but it's like we run these experiments with 4 or 5 students, so it's small tabletop experiments. What's the distance scale? This is about a 3-meter table, 3 meter by 1, something like that. Yeah. So yeah, and this I mean, there are like thousands of elements on this table. Okay, and each one is quite expensive actually. Yeah. And as I say, right, so the students when they come in, I mean, they immediately want to turn on one of the mirrors here. Yeah. So this is like, for example, this is a mirror holder. There's a mirror in here, and with these knobs you can turn the angle of the mirror that we use to align the laser beam. And if you just turn one mirror, then the whole experiment doesn't work anymore. Then the poor graduate student has to find which mirror to turn. Okay. So that's a challenge, as you can imagine. This is this glass cell I talked about. This is where we can hold the atoms in vacuum in the end when we do this cooling to the BC. And what I really find remarkable, there's nothing quite. We don't have any kind of liquid nitrogen, anything cold. Everything is at room temperature. You can touch everything here is at room temperature, but just a millimeter behind this glass wall, we have this microkelvin, nanokelvin temperature. So that's really remarkable. And maybe just thinking about it is mind-blowing. Okay, now let me turn to another story of how we can actually emulate materials with these Bose-Einstein condensates. And the idea of doing that is basically trying to zoom in into matter in a very new way. So here I've sketched out, you can barely see it, that's on purpose, some crystal. It's so tiny that we even can't see it almost here on the crystal on the paper. But if we could, of course, blow this up by a factor of 10,000, now we have a much easier time seeing what's going on. Okay? And that's exactly what we're doing. That's the idea of what we're doing in our experiments compared to real condensed matter physicists or solid-state physicists. We're creating crystals out of light by interfering again. We're making, as you see, interference is a very important topic in my talk. We're taking 2 laser beams, shining them on top of each other, and what comes out is an interference pattern of light. I'll show you a beautiful one in a second, of bright and dark regions in space. And this periodic pattern of bright and dark stripes in space forms a periodic crystal in which we can trap these ultra-cold atoms. Okay, so here's a picture of 10-inch slabs that he took that shows you this. So he took like 2 beams passing through these apertures. You overlap these 2 beams, and out comes this pattern of light. That's recorded pattern of light. You take 3, and suddenly you get this kind of crystal structure. Okay, you take 5, and it looks even more beautiful. Okay, so that's just light. That's just light interfering, just 5 beams of light interfering. And you can imagine, by interfering more complex patterns, you can generate almost any pattern of light you want. And now what we do is we can actually load the atoms into this pattern of light. And that's why we need the ultra-cold atoms, because the light field is not so strong to hold them. We need these very cold atoms that don't move too fast. We gently place them into this crystal, into this web of light, and then they are held in this crystal of light, in free space. Okay, and that's our crystal. And this crystal has much larger structures, much larger scales than the normal crystal, and we can observe the particles actually with standard optical microscopes and see each individual atom. Actually, let me show you this movie also. It's a nice movie of showing these optical lattices at work, again from Ted Henge in his lab. So he takes these 4 laser beams, first overlaps 2, and looks at the interference pattern with a microscope, and you see the stripe pattern I showed before. So this wobbling about, we don't want that in our experiments. And if you take 4, you see this kind of pattern. Also, this wobbling would not be good for us, but okay, it's here in this experiment. And now what he did, actually, you can see it will trap even more macroscopic particles. So he took like 4 small plastic beads, dissolved them in water. Okay, so these are the plastic beads in water. Now you just turn on the light, and can you see how they're following the light? How they're attracted by the light? So the light really exerts a macroscopic force onto these particles. In 2D, it's even more beautiful. You see how they want to lock into the light pattern? Okay. So it's just the light exerting the force onto these particles, and this is what we make use of with the ultra-cold atoms, how we can trap them in the light bead. And we do this with thousands of atoms, with millions of atoms that can be trapped in these light crystals. And very recently, we've been able even to see each individual atom in these light crystals. So this is now a photo, and now we can take photos with this very good microscope objective of atoms held in this light crystal. So each point you see here now is not the plastic bead, but it's a single atom held in this light crystal. Okay. And you can beautifully see them with a very, very high signal-to-noise ratio, as we would say, so they're very visible to us. We can see them excellent. And you can see different phases of matter that appear. You can atom by atom really record what's going on in this crystal. You can see individual defects in this crystal popping up. You can move individual defects in this crystal. So you can really see on a microscopic basis what's going on in this material and how its properties affected if I change, for example, the crystal geometry, the crystal strength, or the interactions between the different atoms. So one thing I just want to show you, just when you can see these atoms, you also can control them. Just to show you that we can really control them down to the level of single atoms. So we can really go into this crystal of light with the atoms in there and move the atoms around to any position we want. So we can make this box of atoms, this line of atoms, this star. Well, as quantum physicists, we like to make the psi out of 26 individual atoms here held in this crystal, and each of these white spots marks a light crystal point, and when there's this bright fluorescence, there's an atom there sitting there as well. Okay, so now how do atoms move? For example, let's do an experiment. I call this the quantum horse race. How do atoms move in these crystals? So quantum particles move very different from classical particles. So we set up a small horse race. Okay, so these are our horses, the atoms. They're aligned here along a line, and then we let them move in the crystal in one direction only. Okay, so now a normal horse would run in one direction. Hopefully they all run in one direction. Your horse doesn't run in the opposite direction. In quantum physics, actually, the horses do run in both directions, and the rules of the game are even more strange. You're not allowed to look actually which particle, where the horses are, where the atoms are. So this animation is a bit deceiving because you don't know which horse is winning the race until the final moment when you take the picture. Okay, you're not allowed to look before. If you look a lot before, you've destroyed the whole race. Okay, and so we do that. So here's kind of the particles are lined up along this line. They're moving in this direction, and now we let them run, and we record after a certain time. We take a photo of where they occur, experiment. And now, when you repeat this experiment many, many times, you find something actually very strange. So imagine you have a pack of runners. You do this race with the horses or a pack of runners. And usually you have very few fast runners, quite a few mediocre runners, and a few slow ones in the tail like me. And then actually these quantum particles on the lattice, they're very different, as you can see. So if this is kind of the distribution, the probability of having a fast runner, you see that actually there are a lot of fast runners running to the left and to the right, and very few ones actually coming here tailing behind. So there's actually really a large part of the very fast atoms there, which is very unusual and something we don't encounter typically in free space. But you see actually the measurement is in perfect agreement with what quantum mechanics predicts. So if I take this Schrödinger equation, which gives me this orange curve, and compare it to my histogram, this is measured, arrival time of the atoms, it's in perfect agreement and shows us we can study this motion of the atoms in a beautiful way in these light crystals. Something we're doing now is that we're really almost doing arbitrary light patterns, shining arbitrary light patterns onto the atoms. So we're taking something like this projector there and shining patterns of light onto the atoms that allow us to generate arbitrary crystal structures, or to study, for example, what happens when atoms flow through a thin wire. How is there, how do they flow through this thin wire? How is the conductance properties changed as the particles interact differently, for example, flowing from here to here? So this would be your battery, your reservoir, where the electrons flow from here to here. And this is something now you can study in these light crystals with this microscopic atomic resolution. You can also study kind of things you would not have thought about, and I certainly would not have thought about in the beginning. We even learned that we can study things that have relevance, usually at much higher energy scales. You heard about Higgs particles and LHC. Actually, there are something like Higgs particles, different kind, not Higgs particles LHC, but very similar kind of excitations at these ultra low temperatures as well. Okay, and these particles, even they're so slow, they can behave like relativistic particles at extremely high energies. And this was really fun to learn about this, and we could solve actually a problem with this that was a long-standing problem in high energy physics, and trying to understand whether this Higgs particle would actually exist in a two-dimensional world. Something just for the end, for the fun of before we conclude with an application also for you. I told you about temperature. We talked a lot about temperature, right? Cold temperature, zero temperature. But to make things even more crazy, you can also do negative temperatures below absolute zero. Okay, I'm not going to explain it to you. I'm just going to say when we did that experiment, it caused like a strong media reaction. I mean, it even made it into Fox News, and so I mean, it was really absolutely crazy. And this was after New Year's. Now we were totally overwhelmed. This was after New Year, we were celebrating New Year, and then a few days after New Year we had that. And there are a few actually websites explaining it quite well. And the one actually I can recommend to you is also actually a good physics channel. It's from our colleagues at Nottingham University in UK. They have a channel on YouTube called 60 Symbols, where they try to explain complex physics phenomena, and they also explain negative temperatures. And what I looked yesterday, and what I found remarkable is almost 730,000 people looked at this video to try to understand what are these negative temperatures about. And actually, I think the only video that trumped this one was the one, what happens when you put your hand in the LHC or something. Yeah? Okay. So let me finally, to conclude, give you an application. What is this all good for, apart from learning about how these particles interact with each other in complex ways, getting a better microscopic understanding. I want to conclude with an application which is actually very, very relevant to all of you today, and this is about clocks. Okay. So clocks have a very fundamental meaning to everything we do. Is it timing? Is it navigation? Whatever we do today relies on having the best possible clocks. Actually, every time you turn on your GPS system, well, not this clunky one anymore, you have a nicer one today, I have one on my watch here, it relies on an atomic clock in space. And one of the satellites sending precise timing signals from these atomic clocks to you on Earth, to me here. Yeah? So having better clocks actually is crucial to having better navigation, better synchronization, having fundamental physics tests also. That's what we're interested in, of course, also. And if you think about it, what a clock is, it's really two things. It's an oscillator, something that oscillates, swings back and forth like a pendulum, and a counter. So let's say you want to define the second. How could we do that? Well, we could take a mechanical pendulum. I know it swings by once, twice, and we define, let's say after this pendulum has swung 10 times, we say that's 10 seconds. That would be the definition of the second. Okay, we won't do that today because that would be a really horrible definition of the second, but that's actually how these things work. We started out 3,500 years ago with the sundial, then we went to the pendulum clocks, mechanical clocks, then we went to quartz oscillators, faster oscillations, and we're at atomic clocks today, how the second is actually defined. These are like 9,192,631,770 oscillations of this electromagnetic radiation of one of these atoms in this atomic clock. When those number of oscillations of fast have been counted, that's when we turn your clock by 1 second. Okay, so you need a counter to count those oscillations. Okay, and actually it turns out today even better clocks are in the making at many institutions in the world. Of course, our national standards institutes here in the US, PDB, Germany, we have something similar in France, BNM CIRT, are comparable institutions. And it turns out that today actually the best clocks, and this is transparency from my colleague Jonier in Boulder, are actually made by holding these atoms in these light crystals. So these atoms are now our pendulum. The electron clouds can be set into motion, and in order that they not perturb each other, that they don't collide with each other, we like to keep them apart from each other, but we like to hold them very gently. And that's what these light crystals can do for you. Okay, so today June's best clocks are built by loading such atoms in optical lattices, and I think in the very few next years we will see a redefinition of the second being defined by atoms held in these light crystals. So then you can say, okay, I know what these light crystals are about, hopefully. And how good are these clocks? These are tremendously good clocks. Just to give you a number, and I'll put this into perspective in a second, they have what we call uncertainty now of about 10 to minus 17, 10 to minus 18, the best clocks that we have today. And this means actually that such a clock, if we would have set it in motion at the beginning of the universe, 50 billion years ago, it would just have an inaccuracy today of 1 second. It would lag by 1 second. That just tells you how good these clocks are. Okay. And well, we don't know what they're going to bring us, but I think they're going to bring us many advancements in science and technology, and this is all happening in these light crystals that I told you about. All right, this is where I want to end my talk. I hope I gave you an overview about the exciting physics of quantum simulations with ultra-cold atoms, in my case, how we build these, some of the phenomena we're looking at. And this really range not only over condensed matter physics. I told you about some applications in high energy physics that our colleagues approaching me, whether we can't do black hole models and things like that in these cold atoms. So they're really serving as fantastic test beds for really trying to understand, how matter behaves, how collective matter behaves, how these particles interact if we expose them to kind of new environments. And you see, we have really very flexible environments we can expose them to that we can't expose normal materials to, normal particles to. Okay, with that, I'd like to end, and thank you very much for your attention. Questions? So we get the microphone.
what kind of power level are you using in the lasers? Specifically, how much wattage are you using?
Okay, so for the light crystals, it depends a little bit how deep we want to make these lattices. Sometimes the more the better. So typically it can be up to 50, 60 watt, which is not super strong for a laser. I mean, it's dangerous enough that you want to wear your safety goggles. Let me put it like that. So it is dangerous, but it's not like, people who do high power lasers would laugh about these power levels.
Too much.
Because you see, because they're so cold, that's the nice thing. Because they're so slow, they're so cold, we don't need such deep potentials to trap them. Even more gentle potentials are sufficient to hold them in space. Yeah.
In your laser cooling system, how do you sense the direction little buggers are moving? And since they're a cloud, surely they're not all moving in the same direction at the same time, at least in the beginning.
Absolutely. So yeah, both absolutely very good question. So first of all, you're absolutely right. They're moving left and right, up and down, and it's a cloud of atoms. So you have to arrange it such that whatever the atom does, it's always seeing the wind blowing against it. And the way to do that is through the Doppler effect. Okay. So what you actually do, this is a bit more. What you actually do is let me come back to this image and show you what we're doing, that this works. Okay, so you have these lasers, and usually, let me draw a sketch here. So you usually have an atom, and simplify the atom, let's say, has two states. And when a photon comes and interacts with the atom, this photon can get absorbed and excite the atom to an excited state. Okay, so typically we match the energy of this photon to this energy separation here, so that it can be efficiently absorbed. But if it's kind of slightly, what we call reticule, if the frequency of the photon is slightly below the absorption frequency of the atom, okay, what can happen is that then in that case, actually, if the atom moves, let's say the atom is moving in this direction, this frequency of this beam is slightly lower than is needed to actually be absorbed. If I move in this direction, I have a Doppler effect, which shifts my frequency up. Okay, so the atom sees is actually the right frequency, but only because when it's moving in that direction. Okay, let me show you actually. Go back to our ripple tank to show you this Doppler effect. Also has the Doppler effect. Where's the Doppler effect? Yeah. Okay, so you see you have a moving atom that emits waves, and depending on whether you're going in the forward direction or the backward direction, you see the wavelength seems to change. Okay, so this is now a moving emitter, and the wavelength shortens in the direction where it's propagating and lengthens behind. And this is what we're making use of. So we're making use of a clever trick that in that direction the atom is moving, it sees more kind of light now in resonance, what we say, which can be more absorbed now, so the wind's blowing stronger. So I'm not sure. Okay. Okay. Yeah.
Could you do something like the analog to the Josephson effect?
Oh yeah, absolutely, absolutely. That's what people do. So, for example, if you want to have a thin barrier, for example, where you want to study to make a Josephson junction, what you can just do, you can, for example, shine a line of light like this one, like this one. This would be now line of light, but it's a potential. We said light is like a potential for the atoms. So this is like a very thin barrier, and you can put a superfluid of VC to the left of it and a VC to the right of it. And if it would be classical particles, this would be just a wall. The particles can't move through the wall. But in quantum mechanics, you can move through a wall. Okay, that's what we call tunneling. That's something else that's amazing in quantum mechanics. And then you can connect them, and you can connect this, for example, with this thin light wire. And people have been doing that. Yes.
You mentioned that you were using polystyrene atoms. Is that the material you've had the most success with?
No, so the polystyrene, these are just the plastic beads that just for illustration purposes showed you how the light forms. Right. Okay, so what we're using, what we like to use, I mean, people have been using atoms all around the periodic table, but mostly what works nicely are alkali atoms in the first periodic group. So for example, rubidium was great. We like rubidium because all the CD writers, they were still used, nobody uses them today, but CD writers, mass market, high power laser dye is available exactly at 780 nanometers. That was just a coincidence, okay, that they made them at that wavelength. So that was great for us because we could buy cheap lasers for $50. We could have our high power laser, right? But now they're not produced anymore, so we have to stock up on the remaining 780 nanometers diodes. And then Blu-ray was the same thing. Blu-ray dye is also then was good for lithium, so it was kind of a pure coincidence.
And you see them optically because you move them so far apart using the light wave.
That's right. They're separated at micrometer distances or half micrometer distances, so with a good microscope you can see them. And this distance is about 10,000 times larger than what atoms are spaced in a normal crystal. So in a normal crystal you could never use normal light.
Electron microscopy, which destroys the satellite.
You need a good X-ray source, a very low wavelength microscope, and people are building those, but these are expensive machines, and they have limitations. And what's nice here, that we can really see this with optics. And also what I didn't say, next to enlarging the length scales, at the same time all the time scales become extremely slow. So everything that happens very fast in a solid is slowed down dramatically in our light crystals. So looking at the time evolution of what's going on is much easier for us. It's actually trivial for us than for a solid state physicist trying to do that in a real material.
Thank you. I have a couple of questions that are going to reveal.
Oh, really? I'll be there afterwards, so you can ask me all your questions. Okay, afterwards, don't worry.
So the first, I guess then I'll bring it down to my level. The things you have with lasers and beyond the move atoms with the force or the attraction of light or pushing of light, things like that. Can you describe how that can be used to create like a Star Trek transporter?
Oh, no. No. I mean, that's a simple answer. I mean, the only thing I can explain is what these are these propelling spaceships with these sails, light sails, and people have been seriously calculating this, not just science fiction. I mean, people have been thinking about this. Maybe Lars, you know better than me, but I just know this recent Miller proposal to actually propel small satellites, small satellites that are spent in space, and you want to have laser cannons here on Earth that shoot up the light beam towards that satellite to propel it. But I think it turned out that you need a lot of power actually to do that, and many lasers. I'm not sure it's realistic, but something to think about. So you can propel things by light. Yes, you can propel things by light for sure. Yeah, I'll show you. Yeah. Human atoms? Oh, you probably would be heated up before you propelled a little bit further on. That's your problem. Yeah. But if you put a good reflector on you and maybe put you a lot of power. No, you can. I mean, you can levitate. As I showed you, you can levitate. There's a nice experiment we always do. And, you can levitate particles in a laser beam. But usually, it gets scales unfavorably the more massive you become, unfortunately.
So maybe give us a sense for that optical table. You have many of those in your lab.
Right.
When you start a new experiment, somebody has to lay that out.
Yeah. So typically when we start, of course, there's nothing in the lab. These are empty labs. There's absolutely nothing, and we have to build all this, all the electronics. As I said, that's not even the experiment. That's just the preparation table to prepare all the light beams. You see these yellow cables, they're glass fibers that guide the laser light from this table to another table where the actual vacuum chamber is, where we do the laser cooling and the light trapping and everything. Yeah, go ahead. Yeah, so amount of time, typically 3 years to get this going.
With 5 people?
Yeah, 5 people. If you're lucky, if you make an error, 1 year more.
Yeah. How many atoms can you hold at a time at this point? And how long can you hold?
Yeah, good question. So we do this ranging from few atoms, even down single atoms, up to millions of atoms that you can hold in these light crystals. How long do you hold them? Well, you can hold them tens of seconds. So that's plenty of time for everything we want to do. Yeah, that's a good question too. They typically heat up. Eventually, they do heat up, and they boil off. Essentially, they sense that the environment is not really, and the laser beams around them are not really letting them stay cool as we would like them. Yeah, exactly. But 10 seconds really, that's a really enormous amount of time for us to do experiments. Absolutely. So it's plenty of time. We're not absolutely not limited by that 10 seconds. But then, when that happens, or when we even take a photo, we have to go through all the cooling cycles that I told you again. We start with the hot plasma rubidium atoms. We do laser cooling. We do evaporative cooling. We load them into a crystal. We let them evolve. We take a photo. Bang, gone. Again. So that whole process takes about 20 seconds, 20 to 30 seconds. So every 20, 30 seconds we can take a picture. Yeah, sometimes 24/7. Yeah. That's what we try to keep it running as much as we can, to get as much data as we can.
In order to see the individual atoms in fluorescent, is that correct? Is a recoil enough to disrupt the crystal?
Okay, that's a very good question. Yes, so the question is when these photons hit the atoms, so they light the atoms up, that's how we see them, but they also give a kick to the atoms that we talked about, right? That's the mechanical part of the interaction. So that's indeed a problem, and what we have to do is that they really stay in place, that they really stay put, and we want them to light up. What we want the atoms to do when they're in this crystal, we want them to light up to show themselves what they're doing. But at the same time, we don't want them to move during this illumination because that would falsify their original position. We want them to stay put and just light up, okay, where they are, and to reveal their position. And to do that, we actually have to combine laser cooling and fluorescence. So we have to cool them simultaneously while they fluoresce, so that they stay low enough in temperature so they can be held in place by the light crystals. And at the same time, we turn the light crystal power up as much as we can, and that comes to your 60 watts. That's why we like 60 watt lasers. Then we really crank up everything they have. And at that point, we take the photo because they kind of get hotter.
I was just wondering what some of the other applications are. I know you started to talk with quantum computing. Is that another application beyond the...
Well, we're not. You see, quantum computing is, in a sense, is a more even advanced form. I would say if you have a quantum computer, you can do quantum simulations with a quantum computer for sure. It's more universal. But it's something much more complicated. Okay, much.
It's quantum field theory, and that's a theory of elementary particle physics. So the physics would be some kind of a scattering process of electrons, and there's a photon, and there's quarks and gluons. And we generally describe it by these types of diagrams. These are the founding fathers of quantum field theory. Quantum electrodynamics is what they discovered. And what this lecture is going to be about is taking Einstein's general relativity and trying to put it together with quantum field theory. So first, we're going to talk about Yang-Mills theory. So that's a theory. 3 of the 4 known forces in nature are described by what are called gauge theory. Oh, this thing that was claimed to be the best one is a dead one. Let's try that again. Always have a backup plan. Okay. 3 of the known forces of nature, they're described by what are called gauge theories. We talk about electromagnetism. There's the founding father, Maxwell. And then there's the strong nuclear force, QCD. Of course, that David won the Nobel Prize. Of course. The weak nuclear force. And together these two are described by what are called Yang-Mills gauge theory. The generalizations of electromagnetism. There's Yang and Mills. And we have here the elementary particles. So there's the quarks, the leptons, the electron, neutrinos, 3 generations, the force carriers, there's the proton, the gluon, the Z boson, the W boson. Now, let's have a look at gravity. That looks different. It's not based on a Yang-Mills theory. It's based on a geometric theory, curved space-time, and then it has all these marvelous concepts you don't really find in the other theories, such as black holes. And when you when you look at the quantum field theory, then what happens is, first you find gravitons. Those are analogous to photons. I don't know if you discovered a graviton, but we're quite sure they do exist. exist the same way that photons exist. But very quickly you come across infinities, ill-defined problems in the theory. And these types of, call them untamed infinities, they don't occur in this Engels theory. They have infinities, but we know very well how to deal with them. Now, this problem, in fact, these infinities, I'll be talking more about that later in the lecture, but that's actually a problem that's solved through string theory. So that's the most popular way to deal with this and other problems in quantum gravity. But I'm not going to be talking about that. I'll be talking